So yesterday we talked about some gun classifications. Mikrofonlar söndürün. First of all, we talked about the assessment of perforating charge performance. And yesterday, sorry for the confusion about the section 3. Section 3 is, we talked about section 1, what we test. Section 1 testing procedures. Section 2 procedures simulates downhole conditions in the laboratory for penetration lens. And section 3, actually I have to change this slide later. Section 3 test is used to evaluate perforating system performance at elevated temperatures, and this test characterizes a system's function, reliability, and performance degradation at elevated temperature. These tests are typically conducted in pairs, one at elevated temperature and second test at ambient temperature, to use as a benchmark. May incorporate elevated pressure to further verify the operational rating of the system. So as a result of this test, we get penetration depths into the steel target of a shaped charge. So how much due to the elevated temperature is the shaped charge, how the shaped charge will penetrate through the steel target, and face-placed casing hole diameter from each shaped charge, and the hole roundness, how ideally it should be well-rounded hole, but how it will how it will change due to the elevated temperature, how these elevated temperatures affect the perforating performance itself on casing, on steel targets, the penetration roundness, etc. Okay. So then we talked about the classifications. We talked about gun conveyance, the wireline conveyance through casing, through tubing, then tubing conveyed perforations when we do this with the completion installed already into the wellbore, and tubing or coil tubing or Drillstem testing or completion perforation, when we perforate it, test it, produce for a short time, and then kill the well, pull out the Drillstem string or the coil tubing string, and then continue complete the completion with the lower with the tubing string, normal design tubing string for this well. So we talked about the gun types, what are the key point or advantages of different conveyance methods, and today we are going to talk about another classification, which is retrievability of the perforators or gun systems, gun tools. Can you see the slides changing?
Yes, we can see.
Okay, I mean the connectivity problem is okay, right?
Yes.
Voice and slides are Good. So by the retrievability, we have a retrievable gun types, and these retrievable gun types are, as it sounds for itself, can be retrieved to have to have them checked, and they are run into the hole, as I shown before, and we'll show on the next slide. With the carrier and latest developments are the scalloped holes for at the charge spots. These scalloped holes have a very thin covering, metal covering, and this carrier protects the charge from well fluids, well pressure, and temperatures, so they are preserved from any outside effects. It is robust and less liable to damage during running because it's about the charge because it is in the hollow carrier. Fast running speed into the wellbore, again, because it is a closed pipe. We don't have a flexible modules like an expandable charge capsules, and there is no debris because once we shot those charges, all debris stay in the this hollow carrier. So, and then we run it back, and we can check which charges were performed, which charges were shot, and how the performance was of the gun system. So we can re-perforate if we need, or we can rearrange the charge gun arrangement if we need to. So, okay. Disadvantages of this retrievable, as you can see, the gun length is limited because of surface handling problems or lubricator length, and large intervals require multiple gun rounds or use of stackable guns. Again, here we have, if we are running it with the wire line, we have to follow the weight limit of this wireline cable, and for certain charge we may have a exposure time limit because this is the metal case. So this metal case is when it's under temperature, high temperature, the metal case itself will get heat and may cause some if the exposure time exceeds the time allowed for the certain charge, certain explosives charge, the charge may get degraded. Therefore, we have to plan our perforating operations carefully in terms of timing, so we know how long this charge is going to be in the wellbore, and we have to know the temperatures in the wellbore and choose correct or appropriate explosives to avoid any degradation. Yes, Rufat. Do you have a question?
No, teacher, just by mistake.
Okay. Expendables, they are flexible, can be run longer lengths because it is a not so heavy, less weight, and more economical in terms of gun cost and time required, because these guns are arranged around the console type carrier. You can see here, this is the aluminum carrier strip, and the charts are screwed into this carrier strip, and it can be done in different orientation. So it is just a how you stick this into this carrier, aluminum carrier. So during the perforations, these carriers, the guns are self-destruct on detonation because of very high pressure, temperature, and explosion. And these are left in the wellbore. Only some connectors and descorrelation equipment retrieve it to the surface. And the gun consists of a number of charges strung together like here. So as I said, no rigid carrier strip or tube is used. It's just this very thin, very light carrier, and charge case designed to fragment on detonation, friable material. Charge case must be sufficiently strong to protect the charge during the handling operations. It means these are it is about this charge covering, because if something happens to this charge, it will explode at any time. It can explode at any time, and it might lead to very severe consequences, and also tend to create greater kinetic damage than the other guns. It's because it absorbs less of the reaction. Okay, what does it mean? When you run your perforator with this carrier, it is more stable, more strong, and when you shut the charge, when you perforate, the most of the energy reaction or reverse reaction of the charge are absorbed by this carrier. But in this case, it is not taken into. It is a very light construction. Therefore, the reaction from detonation may cause damage, some damage to the casing, if the charge arrangement and design was not properly thought through. Sorry. This is charge for the expandable through tubing gun. You can see here the detonation cord, the primary explosive, the main explosive, the liner, so the shaped charge, and here this is the carrier strip, and this is the coverage to protect the charge. Okay, and this is the charge body charge case to keep everything together. Okay. Retrievable wireline through tubing perforating guns, as we said, they are run into a hole in the steel carrier tube. It is sealed to protect charge and electrical connection from the well fluids. The diameter of retrievable guns steel tube slightly may increase after firing because of high temperature created by the perforations, explosions. Guns maximum allowable diameter to be ½ inch smaller than tubing minimum diameter if it is through tubing. And scallop gun was developed to provide improved perforating performance compared to simple metal tube. As I said, these scalloped holes have a thinner tube wall to allow the charge to create less resistance on the shot on the way of shotting with the perforation charge. So this is the charge for the reusable retrievable casing gun. So the charge might be the same, but here you can see the alignment sleeve of the carrier. So sorry, it's on the charge, and it is the alignment sleeve to stick the charge into this scalloped hole. And this is the port plug. This is the port for the charge, and this is the steel carrier tube. Any questions about the retrievability of the gun system or perforators?
May I ask questions?
Yes, of course.
How about semi-expandable?
What do you mean by semi-expandable?
If I'm not mistaken, there is another type, semi-expandable. I saw in one video that.
I honestly haven't seen this, haven't heard about that. I will get information about this and will let you know what is semi-expandable. Honestly, I can guess that the expendable, it's something that you can expend. You can just live there, so that's expended. It is left there. And semi-expendable, I will find out and let you know. Okay, next lecture.
Okay, thank you, teacher.
Okay. The next classification, as we mentioned before, is the perforation technique, or at which pressure conditions we do the perforations. And the first one, we are going to consider the underbalance perforating. Here we have the extending flowing of the well to remove debris from near perforations. And if the well is equipped appropriately, we can do the well build-up test to obtain some information about the reservoir, like reservoir pressure, near wellbore permeability, some extension around the well, near wellbore zone, etc. Next is dynamic underbalance perforating. This is relatively new, although it is in use for decades. It's a perforating system engineered to create a rapid underbalance immediately upon perforation. What does it mean? It means when we prepare the perforations, before the perforation itself, we have a overbalance conditions, but by the design of the perforation, the well fluids in the wellbore, we can install some equipment that will create very low pressure at the wellbore, at the downhole, so during the perforation, exactly during the perforation, and by that we can create underbalanced conditions, and the fluid at the moment of the perforation will be flowing into the well, so cleaning the perforation tunnel from the debris, from the jet materials, from the crashed rock materials. So we will get very clean, very sorry, very open perforation tunnel. Okay, we'll talk about that later. The next is overbalance perforating, which is the most conventional. People use this to be on safe side when the wellbore pressure is higher than the reservoir pressure, and it is, as I said, it is used to keep the well under control during perforating to avoid any blow up or any kickoff due to the reservoir inflow into the wellbore, reservoir fluid inflow into the wellbore. And the extreme overbalance perforating is also relatively new when the wellbore is pressurized up at very high pressures with gas or other instances, and when the perforating guns are detonated, the inflow of high pressure gas into the formation results in a mini fracs, opening up the formation to increase flow. This is actually done to increase the effective wellbore radius. We will see it in next slides in more details. Let's talk about first underbalanced perforations. As I said, reservoir pressure is substantially higher than the wellbore pressure in this case. So the pressure in the wellbore before the perforations is lowered well below the reservoir pressure or formation pressure, and adequate reservoir pressure must exist to displace. So we have to have quite high energy in the reservoir. So as we perforate, then the because of the pressure difference or pressure drawdown, the fluid from the reservoir will flow into the tunnel, perforation tunnels, and will clean this perforation tunnel from the perforation debris, the crashed materials, etc. So we will get very clean the perforation tunnel, and this will work very well with the when we produce the well with the clean perforations. So it is increasing the well productivity. It is increasing well productivity very substantially. Okay. Dynamic underbalance perforating is perforating system engineered to create rapid underbalance. It creates a rapid surge flow once we perforate it. You can see what happens in static underbalance and dynamic underbalance. This chart or picture shows difference between the three types of perforating. So this one is overbalanced when we perforate the well, and the wellbore fluid is entering the perforation tunnel. So we get, because of this, we get squeezed and crashed zone around the wellbore, around the perforation tunnel, and it is not opened up efficiently. On static underbalance, when the underbalance conditions or low pressure, lower than reservoir pressure in the wellbore before the perforations, we end at the perforations. Once the perforation is done, the fluid in the wellbore goes into the perforation tunnel, and the reservoir pressure pushes the fluid into the perforation tunnel, and the perforation tunnel is cleaned by by those fluids, by this flow into the wellbore. But what happens in the dynamic underbalance? At the dynamic underbalance, the perforation shut, or when the charge is shut, at the same time we create with the gas, with some equipment, we create very low pressure at the downhole. You can see here, this is the dynamic underbalance graph, the graph of the pressure. So at this point, when guns are fired, we get very fast lowering the pressure at the downhole, and this creates flush flow into the perforation tunnel from the reservoir, and this will, and you can see it goes down for a short time, in very short time, and for very short time, and then we get some again the build-up pressure, but for this short time we get a very fast, very flush inflow into the wellbore through the perforation tunnel, and this helps to clean the wellbore. You can see with the dynamic underbalance we get more. The tunnel itself is larger, and the cleaning is much better. And as we done this dynamic underbalance at the perforations, during very short time, we get a very high underbalance, 176 bar for this case, and then the pressure in the wellbore goes back to the normal, so we don't get very high static underbalance like in this case. And this is when the flow goes into the wellbore and up to the well, that might create, if we don't if we kind of design our perforation operations incorrectly, static underbalance may cause some kickoff or blow up into the surface, to the surface. But with the dynamic underbalance, creating very high pressure drawdown at the wellbore will help to clean the wellbore, the perforation tunnel, to get a larger perforation tunnel. And after that, the pressure is built up back to the reservoir pressure, and we have safe system in the wellbore. But the main task, the cleaning of the perforations are done, so we get clean perforations, we get safe well. Okay. Now, overbalance perforating. Sorry.
I'm sorry,
When
Can I
we,
ask a question?
Yes,
okay.
go ahead.
Could you explain the previous graph one more time? There are some unclear points for me.
Which one, on the left-hand side or right-hand side? Well,
Right-hand
these
side.
are the same.
Yeah.
So this is a pressure, wellbore pressure, the pressure in the wellbore, the axis, okay? And this is the time. So this is the reservoir pressure line, the green one. The orange one is the pressure at the when we do static underbalance. So as you can see, for the static underbalance, we have static pressure, initial pressure below the reservoir pressure in the wellbore. And as we start shutting, due to the created high pressure and temperature due to the explosion, some pressure increase is observed, but then due to the total pressure in the wellbore, it goes down and we get some desired pressure drawdown in the wellbore. So the fluid flow into the from the reservoir and through the perforation tunnel to clean the reservoir. Okay. This is when it says slow, it doesn't mean days or hours. It's still a very short time in minutes, maybe. Okay, but still, this is this underbalance pressure or the pressure drawdown is serves for the cleaning the perforation tunnel by the reservoir fluid flowing through this. So we get all the crashes and the crashed material perforation debris out of this panel, tunnel, perforation tunnel. Okay, but when we do underbalance perforation, sorry, dynamic underbalance perforation, this is achieved by the for example, we have some capsules with gas in there, and as we shut the well, as the explosion happens, the same time, at the very same time, as you can see, those capsules or chambers are exploded, and a lot of gas enters the wellbore, and that creates very high underbalance. So that lowers the wellbore pressure, the pressure in the wellbore, for very short time. You can see, and here it's the actual measurement for the 176 bar. This is very, very huge number for underbalance or for pressure drawdown, and it is just for 4.3 seconds. Okay, the duration of this is for just in order of 5 seconds. Okay, and during these 5 seconds, we get very flash inflow from the reservoir into the wellbore through the pressure tunnels, perforation tunnels. Okay, and due to this very high pressure drawdown, very the velocity of the fluid going through the perforation tunnel and the wellbore is very high from the reservoir, is very high, and that cleans even more crashed area, because when we shut the well, we get crashed zones around perforation tunnel. And this flow in for this high pressure drawdown and for short period will clean the well perforation tunnel bore even faster and more efficiently. As you can see, in comparison, this tunnel has this is a simulation, but this tunnel has a larger diameter than this tunnel, okay? In the reservoir, in the rock, okay? Let me show you what happens with the this is what happens with the rock or reservoir because of the perforation. This is the rock before the perforation. This is sand particles, and this is the same rock after the perforation. Okay, you can see how these grains are damaged, crashed, and they are reducing the permeability very much, and this should be cleaned. The small particles, these fractured particles should be cleaned from the perforation tunnel. So the flow of the fluids through the perforation tunnel is efficient, and the obstruction on the flow on the flow passes are removed, so we get smooth flow into the perforation tunnel and wire this perforation tunnel into the wellbore. And believe me, this increase the productivity of the well in very high level, in very high grades. So difference between this perforation and this perforation and this perforation in terms of well productivity is very, very, very significant. Okay. Vishal?
Yes, okay, thank you. One more question related to the previous chart, which is on the right side. Why
Okay.
this, let's say, yellow line, let's say, goes like that, increasing? Yes, I understand that part. Why then it decreases? Then after some point, it again increases.
Well, again, initially, this is actually orange, not yellow. But anyway, maybe on your screen it's yellow. We are talking about this one, right? The static underbalance. Can you see the mouse?
Yeah.
Yeah. So initially we have, as we said, it is a static underbalance. A static underbalance means we have a underbalance conditions before the perforation. So the wellbore fluid, the completion fluid in the wellbore before the perforations creates the pressure that is lower than the reservoir pressure. This is this green line, okay? So you can see this difference or pressure drawdown, okay? Once we shut the well, this is the shut time or guns fired, the explosion creates high pressure and temperature, therefore the pressure goes up. But then when this effect of the explosion goes away, and it's all very quick time, you can see it's seconds, goes up, and then it goes to the original pressure, the pressure value, okay? Do you understand that?
Yeah.
And then once, because it is stable, static underbalance, so there is nothing changing. the reservoir fluid is going into the wellbore, okay, which is heavier than fluid in the wellbore. And because we are not producing, or even if we are producing at high rates, which is not usual, but anyway, the balance between the pressure, reservoir pressure, and wellbore pressure is getting kind of matched. So therefore, it increases because the now reservoir fluid, which is heavier than the wellbore fluid, goes into the wellbore. Okay, and this in this case, it is just the balance between the wellbore and reservoir is achieved. Therefore, this bottom hole pressure is reaching the reservoir pressure and it's balancing. This is assuming that we are not producing the well, but we are perforating it under balance conditions. So just to get some flow from the reservoir to clean the perforations.
Malam,
Well, yes.
could you explain the same things for blue line?
Okay. For blue line, we have the static pressure in the wellbore is a little bit above or equal to reservoir pressure. You can see the blue line. Once we shut the well, once we shut the charge, sorry, not the well. Shutting well is closing the well, sorry. Once we shut the guns or fire the guns, at the same time, the capsules or chambers that will create dynamic underbalance are also exploded, and the some light, very light, or some gases are released into the wellbore, which creates very low pressure at the downhole, okay, in the perforation zones. And this drawdown created in the wellbore can be very substantial, much higher than the static underbalance, which is limited because of the longevity of the operations, and it might lead to the kickoff or blow up of the reservoir fluids to the surface. But in this case, this underbalance or dynamic underbalance, which is created at the moment of the perforation, creates very high drawdown for very short period. Here you can see from the actual data, it's a 4.3 seconds. And in this chart also you can see that this dynamic underbalance is created for a very short period, which is equivalent of the shutting time and the pressure on the downhole pressure increasing time of the for the static underbalance. Okay, and for this short period, the very high velocity fluid inflow happens through the perforation tunnel, which cleans the wellbore perforation tunnel. And as the effect of these gases or the light substances go away, because again the reservoir fluid flows into the wellbore at very high velocity, so therefore the reservoir and the original pressure was around the reservoir pressure. Original wellbore pressure was around or even higher than the reservoir pressure. So as the reservoir pressure rapidly flow into the wellbore, then the pressure in the wellbore is also getting balanced with the reservoir and equalizing with the reservoir pressure. Did I answer your question, or?
Yes, teacher, it's clear. Thank you.
Okay. Somebody was again also questioning, having question. Any other questions? Okay, let's continue then. Well, we started with the overbalance. Again, overbalanced perforating is more conventional, classical, because we want to keep the well under control. So there is no kickoff, there is no blow up to the surface of the reservoir fluids. So what we do, we create higher pressure in the wellbore than in the reservoir pressure, and but due to the overbalance, when we shut the well, when we perforate the well, perforate the reservoir, the fluid goes. We create some perforation tunnel, but this perforation tunnel, because the reservoir wellbore fluid is flowing, following by this perforation, and it seals all the debris, jet, and crashed zones, and even squeezes more this crashed material into the reservoir rock, creating some damaged around the wellbore perforation tunnel. On top of this damaged zone because of the completion and drilling operations. And then we, of course, we will try to flow back this this well to open the perforations, and this will clean up some, partially clean up the perforations, and we will get some area to flow, but still the some crashed zone around the well, around the perforation tunnel will be there, and this material from the jetting will stay there. Okay, so the perforations will be partially still plugged with charged debris, squeezed rock materials, etc. Okay, and of course, again, on top of this damage, we again introduce we flow the wellbore fluid into the reservoir, and therefore even more damage may be created to the rock permeability. Okay. So in this case, we for the carbonates we may use the acids. So the acids entering the reservoir or formation will clean and will dissolve the carbonates materials. So the some additional wormholes will be created, increasing the permeability of this zone. And of course, we have to use very clean fluid to prevent further damage to the reservoir. The next is a extreme overbalance perforating. And this technique involves, as I said before, very high pressures above the fracture gradient of the reservoir. And what happens in this case, once we perforate the well, the pressure above the fracture gradient will create the fractures at the tip of the perforations. Okay, and depending on the minimum stress orientation or fracture orientation, these fractures will be oriented along this minimum stress orientation direction. And you can see what happens here. We create fractures that goes beyond the perforation tunnels, and these are increasing the effective wellbore radius. Okay, and and this increased effective wellbore radius increases the reservoir, increases the well productivity, because as you know, the wellbore radius is a part of the equation for the well productivity, and increasing the wellbore radius substantially, we will get substantial increase in the well productivity. In this chart, you can see the effect of the extreme overbalance perforating on different reservoir conditions, particularly on permeability. Okay, so what you can see here, the least effect of the overbalance is for the 1000 millidarcy or 1 darcy reservoir, and the maximum effect is for minimum permeability of 0.1 or 1 millidarcy. Why is that? Why higher permeability of the reservoir, the less effect of the extreme overbalance? That is a question. Hello? You can write your answers on the chat section. Can you hear me? Hello?
Yes, we hear you. I have one answer, but I don't know it's correct or wrong.
Well, never be shy to answer. You are students, and you may be wrong, you may be right, but you will at least check your is it a correct answer or not? Okay, go ahead.
I think that is low permeability is due to that low permeability comes from the low compaction, and there's compaction is low, and due to that the hydraulic fracturing in the low permeability is higher due to compaction.
Okay, any other? Okay, Vishal is saying because the effect of overbalance, extreme overbalance, is decreased when there is already been sufficient permeability. This is sort of a correct answer, because when we have high permeability, the flow and the high permeability is around the well, and the flow into these perforations or the tunnels are sufficient anyway. So this fracturing will not help that much. You can see there is still effect, some effect, like say more than 10%, which is substantial still. But it is not comparable to the effect when you get more than 100%, more than twice increase in the well productivity or flow rate for the lower permeabilities. So the higher permeability, the effect of fracturing is lower, okay? Because what the fracturing is doing, fracturing is increasing the exposure of the reservoir to the exposure of the well to the reservoir. Fractures are connecting some impermeable zones, but if your reservoir has enough permeability, sufficient permeability, then the fracturing it will not have a great effect. That is why sandstones are not fractured usually, because the sandstones has already enough permeability, and by the fracturing you will not get great effect, and the at least the cost of fracturing will not cover the incremental oil production, oil or gas production. Okay, so thanks Vishal, thanks for everybody, Amil, and let's continue. So we now we are going to talk about the operational considerations. What are the equipment are used? So, of course, as we talked just through, perforating operations are conducted with under or balanced pressure, over balanced pressure, and therefore we have to test our wellhead and the other equipment at the surface. So if the hydrocarbons and pressure reach the wellhead, it is not leading to any blow up or kickoff. So the surface equipment, surface personnel is safe. Okay, therefore we have to make sure that the blowout preventers, any other the lubricator if required, if we are doing the perforations with the wireline, are equipped, installed properly and at correct pressure ratings. So if we or not, we may have some pressures at the wellbore, sorry, at the wellhead, at the surface. So we have to keep this well pressures and fluid flows under control. Okay. Wow, we are running out of time. Sorry. Okay. Let's finish this on the next lecture, or you can go through these operational considerations in your books. Well, let's continue on the next lecture. Sorry, I forgot about the time. Now we are having a FTP discussion session. So, any questions? Let's finish today's lecture at this point. Any questions so far?
No questions, sir.
Okay. Yes, we are going to Canada. Sorry for not following the time. Okay, thank you very much then. See you next week. Now we are meeting with the group number 1. Aytaç Hanım leading group. And then group number 2 at 4. Sorry for taking your time. Too long. Sağ olun.
Sağ olun Kamal.
Sağ olun.